we better solve an interesting problem from chapter 40. I think it's called quantum physics. This chapter introduces the interesting ideas that kind of stumped scientists in the last 150 years that led to the creation of a new field of physics called quantum physics, or specifically quantum mechanics is like the type of math that you use to solve these problems, or the theory that solves these problems. So a lot of the concepts you learn here are, I don't know, very broad in nature, very like different kind of experiments lead to here. One of them is this phenomenon that happens when you heat up shit like metal. You see that it glows in a specific color. This problem is related to that. So we're going to start off reading it here today. Make sure you stay for the whole video. I'm going to give you guys some tips on how to study. We're going to look through the book a little bit, but the goal is solve this problem by the end of the video. So let's read it out. The temperature of an electric heating element is 150 Celsius. At what wavelength does the radiation emitted from the heating element reach its peak? Interesting. Okay, let's color this guy here in red, 150 degrees Celsius. This is a temperature of an electric heating element. All right, whatever. I don't think that's too important. At what wavelength? This is the question that we are being asked. If we give a wavelength, lambda equals some number here, we will answer the question, right? Because that is what the question is asking. At what wavelength does the radiation, this is an important word, maybe I'll put this in green, radiation, emitted, because radiation apparently has a wavelength, right? Because of how this sentence is worded. And the heating element is producing some kind of radiation at this temperature with this wavelength. So this is one of the concepts that we talk about in this chapter. Basically, heat stuff up, it glows. Cool. So people observe this, like dudes making swords, blacksmiths and all that. And some people try to figure out an equation. Is there a relationship between the wavelength emitted by the light produced by these hot objects related to the temperature of the hot object or some other stuff? So that is the question. I'm not going to read too much further into it. Pull up the book here and show you the question. So this is chapter 40, Introduction to Quantum Physics. The first problem under this section here, the temperature of an electric heating element is 150. At what wavelength does the radiation emitted from the heating element reach its peak? So I just want to show you kind of what this question looks like. This is the first question that starts with this heading problems. So this is problem number 1 of chapter 40 in the textbook that we're looking at. If you scroll a little bit up, you'll see there's another section marked by conceptual questions. These are a little different than problems. We have conceptual questions here. We have problems over here. Slightly different. And there is a first section here called objective questions. And then this is the summary of the chapter and the 7-minute summary thing that I did. You could check that video out over here. So I want you guys to notice this is how normally the book is laid out. We have concepts and principles in the summary. Then we have objective questions, which are interesting. We're going to take a look at one very quickly. We're not going to solve it. We're just going to read it. It's followed by conceptual questions, and then it's followed by problems. And then the whole following section is just problems. They actually split up problems by sections. So section 40.1, section 40.2 problems begin here. These are all of them following down here. And you can see all of the sections break up the problems and they give you them here. This is a way you can study, all right? You got to do some of these problems. You can't just magically get all of this information inserted into your brain without doing any of these problems. You got to try as many of these as possible. If you try them, you're going to be boolin'. You got to try them, bro, even if they look scary. And this is why I wanted to quickly take a look at this before we solve this problem, right? The goal of the video is solve this problem here. You can solve any problem you want. Maybe we can do more on this channel, but I quickly wanted to read through just a few of these objective questions and maybe one or so conceptual questions to show you the nature of the problems, right? Because in this video, And in a previous video, most of the videos I do, I solve problems. But these conceptual questions are super important, and maybe I should spend a bit of time doing those. Let me know if you guys want to see that. Right now, I just want to read it out. It's going to give you information, just reading the question. You don't even need to solve it. Let's read the first objective question in Chapter 40, Introduction to Quantum Physics. You ready? Rank the wavelengths of the following quantum particles from largest to smallest. That is the objective, okay? If any have equal wavelengths, it continues here, display the equality of your ranking. Okay, so you have to do two things. Rank wavelengths of certain things, and they give you them here. We have a photon with energy 3 electron volts. So they're basically telling you this thing has a wavelength, right? Because they're asking you to rank the wavelength of these items from largest to smallest. If any of these items have equal wavelengths, then mention that in your ranking. So basically you're making a table. At the top you're writing big wavelength, at the bottom you're writing a little wavelength, and then you're just calculating that and then putting it in this table somewhere. So a photon, they're telling you an item with energy 3 eV. EV stands for electron volts. It is a specific amount of energy. Take a look at the second one. An electron with kinetic energy 3 eV. Okay, so a little bit of a difference, a different thing. Part A we had a photon, part B we had an electron. Part A we had energy 3 electron volts. Part B we have electron with kinetic energy. So slight switch up there. Kinetic is a new word. Interesting. Let's just keep reading here. A proton with kinetic energy 3 electron volts. Okay, electron proton, interesting. A photon with energy 0.3 electron volts. An electron with momentum 3 electron volts divided by c. And that's the end of the first objective question. So it is an interesting question, and it's a bit different than a problem. Basically, all you have to do is calculate wavelength, and it turns out each of these problems gives you an energy. So you can presume, just by looking at how the problem is structured, that somewhere in this chapter, chapter 40, there is an equation that relates wavelength to energy. Otherwise, there won't be any way of solving this problem. So just purely because you read this, you know somewhere in the chapter there's some shit about comparing wavelength to energy. Actually, the section about summary is right over here. And boom, peep this. Wavelength, here we have momentum, here we have mu, which I think you can get energy out of it. Every object has mass m, momentum p, mu. Maybe you can't get energy out of it, but over here they talk about energy, and this has frequency. Anyway, there's some way of like piecing this together. I don't want to solve this problem here, but I just want to show you, just by reading the question and seeing what they're asking you, you can get a lot of information. You can also see words like photon, electron. Here we have photon again. Here we have proton. We have electron volts. Interesting stuff that just by reading, you don't even have to solve it. You just have to read it. You get information about what the class is going to be about, what you might see on the exam. Read this shit whenever you have free time. On the bus, on the porcelain throne, when you're in bed, anywhere, just try to get a bit of this. And if you're interested in it, you can further your studies by watching a YouTube video, asking ChatGPT, Wikipedia search, check a solution, but at least read it. And then if you want, you can try solving it on your own by just digging through the book. Okay, so that being said, if you want, you can read more of these here, but I just want to take a look at one of the conceptual questions too. The opening photograph of this chapter shows a filament of a light bulb in operation. Look carefully at the last turns of wire at the upper and lower ends of the filament. Why are these turns dimmer than the others? Interesting. This is literally just a question. And what they mean by the opening picture is over here where the chapter begins. This filament is what they're talking about. Let me see if I can annotate this real quick. Boom. So this whole thing here is called a filament. It is the thing that chills in a light bulb, that glows and makes light, which actually relates to our question. Anyway, they're saying this specific part has a certain brightness. Let's call it brightness, capital B. And over here, the last couple turns, you can see they get a bit dimmer. Maybe you have brightness lowercase b, who knows? And this brightness is less than this brightness here. So they're basically asking you, like, why is this the case? Over here, you actually see no brightness at all. uh, bright equals 0. So why is that the case? Why is this entire thing here not bright? Why is it only this main part of the filament, and then as you get here, it gets dimmer? Keep stuff like this in mind when you're going through the book and you're just reading stuff, and try to read it as often as you can so that you can remember it. So now that we're at the start of the chapter, we can kind of sweep through and see if there's an equation that relates wavelength, lambda, to temperature, T. Normally temperature is T. If we find that equation, we should be chilling. Blackbody radiation already talks about things that are glowing, so we're kind of in a good section. Total power of the emitted radiation increases with temperature. Okay, we're close. We're talking about power, not wavelength, but this is exactly what the problem is talking about. So if you read a bit of this theory, the problem should be like possible to solve just by looking at some content in the book. Don't go to the solution, try to work it out on your own. You got this. Here we have the temperature T and some other stuff. This is a little sigma A lowercase e, and then we have power on this side of the equation. And temperature to the power of 4. Temperature here is a capital T. Okay, let's check this. The peak wavelength distribution shifts to shorter wavelengths as the temperature increases. I think this is exactly what we're looking for. The peak wavelength. Let's peek the problem. Yes, check this out. Peak. At what wavelength does the radiation emitted from the heating element reach its peak? Wien's displacement law. Is it really this simple? Do we just have this singular equation? This equation doesn't even look too crazy. I thought we were gonna have to use some crazy function like this, bro. I thought just from my kind of memory, I remember this graph here, and I was like, okay, I know there's a peak somewhere for different. You see how there's different temperatures here: 4,000 Kelvin, 3,000 Kelvin, 2,000, and then the peak changes. For 4,000 Kelvin, the peak is closer to 1. For 3,000, the blue, it kind of shifts closer to 1. For 2,000 Kelvin, it shifts kind of between 1 and 2, like micrometer wavelength. So I was like, okay, I know there's a function related to that, and I know it looks like some crazy shit, like all this stuff over here with wavelength to the power 4 on the denominator, and temperature, and we have intensity, like what? But it doesn't even go this far. We straight up have a peak wavelength equation here. So we have wavelength max times temperature equals a constant. You can tell it's a constant because, well, is it a constant? Hold on. It is a constant because here is just a number. This 2.898 times 10 to the negative 3, that is just a number. Over here we have m for meters because on the left-hand side of the equation we have wavelength, which has units of meters typically. And then we have K, which is the unit of temperature, which is Kelvin. So lambda times T is equal to a constant. That means, I'm going to straight up write this down. Lambda max times T is equal to a constant. This is Wien's displacement law. Is that true? Let me peep. Wien's displacement law. What is the constant? 2.898 10 to the minus 3. Cool. Equals 2.898 10 minus 3. This is meter Kelvin. Interesting. So I'm just writing this down because Wien's displacement law, like, maybe I won't remember exactly this equation. Maybe I'll forget it, but maybe I'll remember something like Wien's displacement law. I don't know. It's just names stick out to me. Anyway, when I'm reading through my notes to study for the final exam and I have a problem like this solved, I can peep it. I can be like, yo, Wien's displacement law. I remember that's something related to this. Like, it just brings back memory. So just write that down. When you go to the equation sheet, they might mention some stuff about Wien's displacement law. Anyway, whatever you find, like whatever way you kind of have of personally remembering stuff, try using that. Personally, I like names, associating names with equations. If I remember an equation, I can very easily tell what it is talking about. Boom, boom. We have lambda, we have temperature. So Wien's displacement law, for sure, I'm like, okay, lambda, temperature. If I need something related to those, I know Wien's displacement law has something related to that. Interesting way of studying. So that being said, I'm going to just try it. I don't know if it's exactly the correct way of solving it, but this is the first thing I saw, so I think we're chilling. The only problem is If we go back here, the temperature here is given in Celsius. And here we have Kelvin. So I can already tell that this temperature must have units of Kelvin. Otherwise, there will be no cancellation here. We're going to have units that have Kelvin and Celsius in it, so that's a problem. But that being said, I can at least start kind of writing some stuff. Let's pick a blue color here. What I'm solving for is lambda max, which equals 2.898 times 10 to the negative 3 meter Kelvin over some kind of temperature. And this should have units of Kelvin. If it has units of Kelvin, this Kelvin and this Kelvin cancel. We have meters, and wavelength will have units of meters. This is just some stuff I'm thinking about here. Maybe I'll leave those scratched out. But the question is, what is the temperature? So we already know this temperature equals 150 degrees Celsius. The question is, how do we get this to Kelvin? So at this stage, you can literally just Google search, how do you convert Celsius to Kelvin? I will do this because this is some type of shit you do not have to remember. Conversions, like, maybe it's important to know, but you'll see sometimes when you have really important conversions that you have to know, like degrees to radians. You may have seen that in the midterm equation sheet, or Celsius to Kelvin. Normally they'll give this to you. Like, it's not important for you to remember some goofy thing like this. It's not goofy, it is important, but you need to dedicate the space in your brain for remembering important shit, like Wien's displacement law, how this shit works, what this phenomenon is actually talking about, temperature, heating elements glowing at some specific. You have to know a bunch of other shit. You don't really need to remember Celsius to Kelvin conversion. But since I have done a problem like this many times, I can kind of guess. And like, I want to do this because it's good to train your memory like this. Eventually you'll remember stuff like this. I think 237 Kelvin equals 0 degrees Celsius. I think I just kind of remember this. I don't know if this is true. I'm going to peep on my phone. Let me check Google Celsius to Kelvin. I'm just Googling this. And we have, damn, brother, this is like that dyslexia. It's 273.15. But normally you forget about this 15. 273 Kelvin equals 0 degrees Celsius. So a little bit of a goof up, but you see, even the goofy shit that you don't have to remember, you can kind of test yourself. And eventually you'll try to remember. So 273 equals 0. So how do we get to 150? Basically, we do 0 plus 150 here. This gives us 150 Celsius. What we do on the left-hand side, we do on the right-hand side. I do not want to do addition in my head right now, so I'm going to do 273 on my calculator plus 150. This is 423 Kelvin. Interesting. 423 Kelvin. Not too hard, right? Now we have an interesting equation. I'm going to go back in my blue. Lambda max equals 2898 decimal place right here times 10 to the minus 3 meters Kelvin. Now we have the proper units. 432, a little wonky 2 there, Kelvin. Red cancels here. I still have my calculator. I'm going to 2.898 times 10. 10 has a power of minus 3. That is 0.002898. That entire number divided by 432. Is this true, or is my calculator geeking out a little bit? Let me do some backspaces and put brackets around this, because I'm just kind of tripping out over here if I'm doing this right. Okay, I guess this is what we get. You always want to ask yourself, is the answer I'm getting within reason, right? If you're calculating a velocity and you're doing a mechanics problem, the car is going X meters per second or kilometers an hour, whatever, and you get that it's going like the speed of light or something, you got to be like, okay, hold on. Or it's going negative. I don't know. Maybe negative makes sense. It's going backwards or something, but you got to just ask yourself, does this make sense? So we're talking about wavelength here. This is meters. This equals wavelength max. The peak wavelength. Let me put this in a red box right here. Boom. Put this, some stars around it. This answers the problem, but is it correct? Well, if I go back to this picture and take a look at this, take a look at wavelength here. It is written in micrometers, and we can see in the graph over here, the peaks are around 0.81 or 1.5, like around 1 micrometer. So the general range of these are 400 4,000 Kelvin, 3,000, 2,000 Kelvin. So if you go much lower, this should still be in the micrometer uh, range, right? Micrometers. What we have over here is meters, right? We have meters. So we have 6.7 times 10 to the negative 6 meters. Is that roughly equal to 1 micrometer? That's a question I'm asking just because I'm looking at this graph over here. This is a graph in the book. If this answer is around that range, then I can kind of say, like, I have a graph to compare this to. I can kind of say, okay, you know what? I think I'm actually kind of chilling. I think I'm close to the right answer. And it's very useful to do this on an exam because in another question, they might actually give you some information. They might say in the very next question, light with 4,000 Kelvin emits a wavelength at uh, like 1 times 10 to the negative 7 meters or something. I don't know, something like this. So you might be like, okay, this negative 7 is kind of close to this. This is close to this answer. So it kind of makes sense. I don't know. Just corroborate your shit with the rest of the exam, guys. This is a tip I have for you. This is what I've done. You may see sometimes the answer to your question is in another question. Always read the exam and then go back, check your shit, see if it looks good. So the final thing I'm going to do here before checking if this is correct is convert 6.71 times 10 to the minus 6 meters to micrometers. How many micrometers is this? Okay, so how I remember this is micrometer is times 10 to the negative 6 meter. Yo! Okay, I literally just remember this. I remember there's a graph that goes times 10 negative 6 equals micro, times 10 negative 3 equals milli, times 10 to the 0 equals the blank, like whatever, times 10 to the 3 is equal to kilo. I don't know. There's a graph like this. I'm gonna post it on the video right here. This is kind of just how I remember it. So you can see that this is exactly this. So we can say that this is around 6.7 micrometers. Okay, interesting. Let's check. It kind of makes sense. Imagine 2000 has a peak around 1.5. If we lower it all the way to 400 Kelvin, right? Because that's what our object is at, then this actually kind of makes sense. Okay, now I'm gonna go to the book again. I'm gonna go to the book, go to my bookmarks, go down here to the solutions. This was chapter 40, answers to odd numbered problems. Damn. We don't have an answer. It starts with here 6.85. Interesting. I got 6.71, and over here the book is saying 6.85, and then it has a little blank, and then it has meters, which is infrared region of the spectrum. And then it goes number 3. So I think this 6.85 is the answer to number 1, and then my book was just a bit corrupted. But here's what we can do, guys. All right, guys, it looks like we're chilling. I couldn't find an answer in the book. It says 6.86 here, and in the book, it says 6.85, and I'm assuming over here it's supposed to say micrometers. The book just missed out micro, maybe because it's like right here between the 5 and the M. Maybe it's a complicated symbol. The book was geeking out or something. So I went to ChatGPT, and it says 6.86 micrometers. Keep in mind, ChatGPT is not always correct. It might make some kind of calculation error. But it looks like they both got 6.85, 6.86. And I, in my solution, got 6.7, 6.71. So maybe there's a small calculation error. Maybe I'm geeking. Maybe they actually used, remember when I said conversion between Kelvin and Celsius was 273. It's actually 273.15. So if you do that 0.15 in there, 2.898 times 10 to the minus 3, whoops, times 10 to the minus 3 equals this, divided by, this is 432.15. Ooh, I still get, wait a second. Yeah, bro, I still get 6.7. So I'm not too sure what that discrepancy is, but I'm gonna say it's all right for the purposes of this video. So I hope you guys enjoyed this problem. I hope I was able to give some value in how you guys study. Please try this technique out with any and every problem that you see. Try to challenge your brain. If you're stuck after a while, don't stress, bro. Check a solution. Check ChatGPT. ChatGPT basically used the same thing we used, which was Wien's displacement law. But as you saw, I just kind of swept through the book and I was able to find what we need. That's how these books are made, bro. Sometimes they might give you a question that really challenges you and the solution is found nowhere in the book and you really have to create it from scratch on your own. But as you can see, if you start with the first problems, it kind of builds you up to that and you're able to do it on your own. Don't stress, bro. You have the abilities to do this on your own. You can do it. You just have to do it over and over and over again. Baby steps. Do not feel bad if you don't get something right and just give it another go. Obviously, take some breaks. Don't do physics all the time. Drink some water. Take a walk. Honestly, read a problem, take a walk, come back. You're going to solve it in 1 minute, I promise you. I hope you guys enjoyed. Check out my other videos for a bit of a theoretical read through. And let me know in the comments if you have any questions. I love y'all. Peace.